This is a video on a really cool theory that I learnt about actually when I was just before I started high school. I read up on this called quantum electrodynamics. QED for short. QED. Now, the HC physics syllabus isn't really explicit with this, but it's just good to know for when looking into particle physics. So what's QED? What's quantum electrodynamics? Best way I can define it, it's a branch of physics that describes the interaction between light and matter. Okay, light and matter interactions. Okay, at the most basic level, most fundamental level. It helps us to understand how electrons, photons, and other particles interact with each other. Okay, so quantum, term quantum means tiniest of scales, the scales of atoms and subatomic particles, in this case subatomic particles. Electro, think of charged particles. Okay, dynamics, movement, okay? So the movement of charged particles at the tiniest of scales. So at its core, QED combines two fundamental theories of physics. So it combines quantum physics, quantum mechanics, a theory which describes subatomic particles and atoms, and electromagnetism. Okay, the theory of light. Okay, so understanding how particles behave, charged particles behave, on the smallest of scales. So the theory of quantum electrodynamics was actually put forth, was first created by the English theoretical physicist, Paul Dirac in 1928, where he came up with this equation, this wave equation, describing the motion and spin of electrons. Okay, so electrons, the picture of electrons, the modern day picture of electrons, according to quantum physics, they're waves. Okay, they're probability waves. You can't say for sure where an electron is. You can only say it might be here with, let's say, 95% chance, might be 10% chance here. Okay, so electrons are waves. And Dirac came up with a great equation to describe, called the Dirac equation, to describe how the electron behaves and its properties. It was then later refined, and it was completed by these great men: Richard Feynman, world-renowned physicist, Julian Schwinger, and Shinichiro Tomonaga, okay, in the 1940s, late 1940s. And these three men won the Nobel Prize for their work on quantum electrodynamics in the 1960s. But it was Feynman in particular who took this maths and made it into something a bit more digestible, a bit more understandable in terms of pictures, in terms of graphics. He developed, and they're now called Feynman diagrams in his honor. Okay, so a Feynman diagram shows particle interactions. It's a graphical representation of particle interactions. And they provide a way to calculate the probability, what's called the probability amplitudes of various processes involving particles. So the likelihood that a certain interaction between particles will happen, in other words, okay? So in a Feynman diagram, you've got an X and Y axis. On the X axis, you've got space. On the Y axis, you've got time. And fermions are represented by a straight line. So for example, the electron, say an electron. Bosons are typically represented by wavy lines, by curves. And because the Higgs is such a special particle, the Higgs boson, the particle which gives mass to all the other fundamental particles in the universe, it's represented by a dashed line. The simplest Feynman diagram is that of two electrons, okay? So suppose you've got two electrons, okay, coming together, coming nearby in space. Okay, this is an electron. Now, from basic physics, when you have two particles, two like-charged particles, so two negatives or two positives, they repel. And that's what this diagram is showing. So the two electrons come close together, they repel. There's a point where they repel one another. And Feynman showed that this is only possible if they exchange, represented by this curvy line, a photon, a particle of light. And this photon, it's worth noting, is called a virtual photon. Virtual because it's not real. You might ask, well, how does that make sense? So virtual photons, or virtual particles for that matter, they're basically convenient mathematical tools to represent the interaction and exchange of particles. Okay, they're not actual particles that exist. Okay. These virtual particles, they can have mass or energy so long as it satisfies something called the uncertainty principle, put forward by the German physicist Werner Heisenberg in the 1920s. So these virtual particles, they exist for a very short time. Okay, virtual photons exist for a very short time, but they're not detectable because they're very short-lived. Okay, they make the maths work. So that's a Feynman diagram there. So that's quantum electrodynamics. Now I'm going to talk about something called quantum chromodynamics. QCD for short. So quantum chromodynamics, chroma means color, is the theory of the strong interactions, the strong force. Okay, the strong force is what holds together quarks in a proton and neutron. Here's a proton. It's got two up quarks, one down quark. And these are held together by gluons. Okay, gluons are bosons. They carry the strong nuclear force. And unlike electric charge, there's something called color charge. Okay, sorry, I should say, quantum electrodynamics proposes that, or one of its assumptions is that charged particles, they carry charge, right, plus minus. Quantum chromodynamics, the equivalent of that is color charge. What's color charge? It's nothing to do with the visible colors. It's just a convenient naming convention for a mathematical system. Okay, it just helps physicists keep track of quarks, let's say. Okay, and the thing to note is that color charged particles like quarks, they can't be found individually. Okay, quarks are what's called confined. They're confined. They come in groups. They come in pairs. The minimum that a quark can be found is in a pair. Okay, that's the minimum state of a quark in a pair. It can come in triplets, just like a proton or neutron. There are things called now tetraquarks as well, and so on and so forth. And when you put together quarks, they become color neutral. So for baryons are 3 quark composites, like the proton. Baryons are made of 3 quarks. Okay. The colors are, possible colors, red, green, and blue. Okay, these are the equivalent of plus or minus. When you put these colors together, you get a color neutral system. Mesons, a meson is made of 2 quarks, a quark and an antiquark pair. Okay, antiquark is the antimatter equivalent of a quark. It's got the opposite charge, so it's got all the same properties as a normal quark, but it's got opposite charge. A meson, you can have, let's say, red, for example, and anti-red. Okay, and that'll cancel out to give you a color neutral system, color neutral particle. And there's a really cool phenomenon that occurs. It's known as asymptotic freedom. Asymptotic freedom. Okay, this was proposed by 3 physicists, Frank Wilczek, David Gross, and David Politzer. Okay, and they won the Nobel Prize in 2004 for their work. They worked on asymptotic freedom in the 1970s. So what is asymptotic freedom? Well, let's suppose you've got 2 quarks, 1 quark here, 1 quark here, and they're very close to each other. Now, at this short distance, the strong force between them is very strong, okay, and they're tightly bound together. Now, as you start moving the quarks further apart, something interesting starts to happen. Okay, the strong force between them actually becomes weaker. In fact, as the distance between the quarks increases, the strength of the force decreases. Okay, and this is called asymptotic freedom. Okay, freedom is in the sense that eventually the quarks can separate from one another momentarily. And this discovery by Wilczek, Gross, and Polzier was very important because it helped explain why quarks are always found in bound states, like protons and neutrons, okay, and not as isolated particles. So quantum electrodynamics and quantum chromodynamics, these are two very important quantum field theories, as they're called, in helping us understand how the standard model of particle physics works.